Okay, good morning, everyone. Welcome to session 4B, low power and energy efficient computing. I'm the session chair. My name is Lu Pian. I'm a professor with Louisiana State University. So we have four papers here. We have two short paper and two regular paper. The first paper will be presented by Jonas Martinen. And let me click his video. He's currently a PhD student in Cambridge University.
My name is Jonas Martinen, and this is the presentation for our paper, Programmable Dictionary Code Compression for Instruction Stream Energy Efficiency. First, I will go over the background, then I'll introduce our proposed method. I'll go over some results, and conclude the presentation. First, a bit of background. The instruction stream in a processor can effectively be thought of as an overhead. It doesn't actually contribute to the computations. The instruction stream can constitute up to 40% of total system energy in some cases. A field of study of code compression aims to represent often occurring instructions with fewer bits compared to their original format. Our proposal is to use code compression as a method to improve energy efficiency in embedded systems. For this, we propose to use runtime programmable parallel dictionaries. As previous work has noted, overheads of dictionary compression are relatively low when compared to statistical methods such as HUB. A common approach in previous works is to program the dictionaries or dictionary once a program starts to be that. Runtime programmable dictionaries are more flexible, so you can change the content. We then select our regions to compress, followed by creating dictionaries for each of the compression regions. We then insert control code, which in our case are special header instructions telling how much to fill to each dictionary. Finally, since we are dealing with code compression, we have to fix branch target addresses, after which we can finish the image. When the compressed image is loaded into the instruction memory, it looks like this. We have headers, which tell how many entries are followed by it to be programmed into dictionaries. After the entries, we are free to interleave uncompressed and compressed code, shown here. This is what a compressed bundle looks like. It is simply a number of instructions fixed at design time, and each instruction merely consists of indices to all of the dictionaries. And this is how the instruction fetch hardware looks like. We have a number of dictionaries in parallel, and for each of them we can configure their number of entries and the width. During execution, we can either fetch uncompressed or compressed instructions. We evaluated our method in an embedded system scenario using zero RISC-V, which is a RISC-V core. We compared with two different compressions. First, First, the RISC-V compressed instruction set, and the state-of-the-art method in the field of programmable dictionaries. And here's the evaluation setup. We first have an instruction memory scratchpad, optional instruction cache, connected to the zero-RISC core, where we have an instruction fetch and decompressor. Here are results for the dynamic compression ratio. On average, the RISC-V compressed instruction set performed the worst, resulting in around 18% reduction in the fetched number of bits. Our method was followed by it with around 30% reduction in fetched bits. Slightly better was the method by Turesson et al. However, if we take a look at the runtime overhead, we can see that the method by Turesson et al. Performs significantly worse. And this is due to them compressing all of the instructions in the program image. As we talked about before, this can lead to excessive overheads when inside loops. If you have a programming instruction inside a loop, you will always have the overhead in each iteration. Since we do the programming before program hotspots, we're able to reach on average around 1% overhead. Of course, the RISC-V compressed does not have this overhead since it doesn't program any dictionaries. And the overhead you see here is due to compiler differences between the RISC-V compressed and normal. Results for energy consumption are presented here. Here we present numbers for the core, dictionary, cache, and instruction memory. As baseline, we have the zero-RISC with no cache, shown here on the left, followed by 3 different cache configurations, not using the compressed extension. As you can expect, the instruction cache lowers the energy consumption, except with a very small block size, where the cache is constantly missing and the energy consumption is decreased. With the compressed extension and no cache, we can see that on average, we can save around 10% of the system energy. When incorporating a cache, we can lower the energy consumption further. With our proposed method and no cache, we achieve around 15% reduction in system energy consumption, which is 5% better than the RISC-V compressed extension. We have proposed programmable code compression scheme to minimize the dynamic compression ratio and improve system energy efficiency. Our proposal is to selectively compress instructions while keeping the overheads low, fetching each instruction with only one fetch. We also propose to program dictionaries outside of program hotspots with the help of our compiler analysis. In an embedded scenario, our method reduces system energy consumption by 15%. Compared to RISC-V compressed extension, the reduction in system energy consumption is 5% on average and 21% in the best case. Thank you for your attention.
Okay, do you guys have any questions? Thank you, the speaker. Do you have any questions for him? Okay, let me ask you a question if no any questions. So how did you choose the bundle size of these instructions?
Right, can you hear me?
Yes.
Perfect. Okay, so basically we exhaustively tried these different bundle sizes, and basically the results started to worsen with bundles larger than 3 instructions. But after this paper, we have actually experimented with a long instruction word architecture, and we see the similar behavior there. But yeah. Okay, thank you. Yeah, since our time is limited, let's move to the second paper. Okay, so if audience have other questions, they can type your contact with directly. So the second paper is let me open it first and share the screen. Okay.
Okay, the second paper is an open source scalable thermal and power controller for HPC processors. It's a group of authors from what's the university? And the speaker is Giovanni. Okay, so welcome.
Welcome everyone, I'm Giovanni Bambini and this is the presentation of the paper An Open Source Scalable Thermal and Power Controller for HPC Processors. It was partially financed by the European Union's Horizon 2020 Research and Innovation Program, European Processor Initiative. In the last decade, processors in the HPC sector have evolved to be more complex and heterogeneous, with an increased number of cores. Alongside, also the demand for energy efficiency has increased. To meet these requirements, processors in this field embed dedicated hardware resources called Power Controller System, PCS, to control the power consumption dynamically, to prevent thermal hazard, and to ensure the TDP budget of the power. With the more complex processor and stricter requirements, also the PCS has to be more sophisticated and powerful. We designed a PCS with open source software and hardware, featuring a simple and modular firmware design based on an open source real-time operating system. The hardware platform is based on the PULP control design, running a main RISC-V core supported by a multi-core accelerator with 8 smaller RISC cores. It has a lower power consumption if compared to other PCS in the market, but its advanced design and its computation power allow the implementation of complex control algorithms and the utilization of the RTOS. The control algorithm is divided into 2 main blocks in a cascade design. One block is responsible for the power capping of the chip, and it uses an algorithm based on the thermal room available on each core, and doing so it privileges the more demanding cores. The other block is responsible for controlling the temperature of each core. It features an independent PI for each core, which acts only to reduce the core power, namely the frequency and voltage, if the temperature is approaching the thermal limit imposed by the technology design. The computational power of the PCS allows to run the power dispatching block every 1 millisecond and the thermal capping every 500 microseconds, but it can go even faster if needed. Other blocks and features may be added to the control design, such as the model adaptation to improve the power capping performances, and some machine learning to improve the choice of the operating point, predicting the type of workload that is going to be executed. To measure the overhead of the RTOS and the performance of the control, we tested the firmware and the control design in an hardware-in-the-loop test, using a commercial PULP-based microcontroller as the PCS hardware, and an STM Cortex-M4 to simulate the power and thermal model of an HPC chip. The overheads of the RTOS are 6% of the total available cycles, measured in a 1 millisecond interval, and grow to 11% if we consider also the semaphore lock. We need to improve a bit the RTOS implementation there. The power dispatching algorithm, when compared to a naive equal power dispatcher among cores, improved the budget utilization of 13.7%, with an average higher frequency of 700 MHz up to 1.8 GHz of the more demanding core. The right graph shows also good performances regarding the overall control, with 41 milliseconds maximum overshoot of 1 degree Celsius over the lower thermal limit, and also respecting the power budget and trying to maximize the frequency. Thanks for your attention, and if you want to check PULP or Happy project, you can check the links in the slides.
Okay, thank you very much. Does the audience have any questions to him? No question? Then I can find a question to to you. So Giovanni, you're here, right?
Yes,
So,
can you hear me?
okay, yes.
Hello to everyone.
Yes, which are the benefits of using an RTOS?
First, RTOS simplify a lot the design of the firmware since he manages all the tasks. And also we can execute various part of the control algorithm almost simultaneously by exploiting the preemption of the RTOS, and also improve a lot the code modularity, upgradability, and maintainability.
Okay, yeah, sounds good. Thank you very much. So again, if the audience have questions, please contact with him after the meeting. So we'll move to the third one. Okay, let me hold it first.
Hello everyone.
And then share the screen.
This is Sandeep Tirumala from Purdue University, and today I'm going to talk about our work on IPSM, where we enhance the energy efficiency of intermittently powered systems with compute in memory based on the emerging ferroelectric transistor technology. Intermittently powered systems harvest energy from ambient sources such as solar, thermal, RF, and vibration. The energy harvested is stored in an energy management system such as batteries or capacitors, which are then used to drive several applications like wireless transmission, microcontroller, or sensory measurements. Now, traditionally, polynomial computing architecture has been used for IPS, where we have a memory unit outside the logic unit, and to perform processing, the logic unit fetches data from the memory unit and stores back the results to the memory unit. However, with the emergence of the big data or IoT era, data-intensive workloads have come to the forefront, which has led to what is known as memory bottleneck due to the long-distance data transmission between memory and logic units. Moreover, wireless communication in these energy-constrained systems has led to severe energy and performance inefficiency. And also, as the name suggests, the computing itself is intermittent due to the unreliable nature of the power source in these systems. Now, the key solution to overcome these challenges is to reduce the energy consumption in various aspects of this system. Now, to overcome the memory bottleneck, people have looked at an alternate computing architecture known as computing in memory, where we perform logic operations within the memory unit. Such an approach eliminates long-distance data transmission between logic and memory unit, leading to low power consumption and high performance. Now, several research groups across the globe have looked at computing in memory using CMOS as well as post-CMOS emerging NVM technologies. However, they have not been optimized for IPS or their workloads. So to that effect, the key idea of this work is the proposal of a non-volatile compute-enabled memory fabric exploiting the unique attributes of ferroelectric transistors featuring computing in memory for two major intermittently powered system specific workloads, namely cyclic redundancy check for error detection and edge sensing in wireless sensory networks. Now let's look at what the FET memory consists of. So FET itself has an FE layer integrated in the gate stack of a regular transistor. The transfer characteristics of FET exhibits bistability at VGS equal to 0, depending upon the polarization stored in the ferroelectric layer. FET exhibits several advantages, such as FE materials like hafnium zirconium oxide showcases excellent scalability and CMOS compatibility. They have high distinguishability between their bistable states, and the separation of read and write paths leads to design flexibility. Now, in this work, we look at a 3T FET NVM design, whose schematic has been shown here, where we have two access transistors corresponding to the write and read operations. Now, to read, we sense the resistance of the ferroelectric based on the polarization stored in the FE layer. And to write, we use a two-phase operations to eliminate the use of negative voltages. And based on the voltage at the write bit line, we either store a negative or positive polarization corresponding to bit 0 or 1. Now, using this 3T FET NVM, we design a compute in memory array with the help of enhanced peripherals. The enhanced peripheral consists of a modified sense amplifier, which is an all voltage based sense amplifier for both standard read as well as sim operations. We also have a low power compute module attached to the modified sense amplifier to perform other logic and arithmetic operations. Bitwise Boolean logic are computed at the bit lines using the concept of multi-word line assertions within the computed memory fabric. We also enable immediate XOR operations between a stored input operand and an applied operand. And addition, subtraction, comparison can also be performed using the enhanced peripherals of the proposed compute in memory fabric. Now, we also propose a novel approach to perform in situ comparison in memory. An example has been shown here for two words. We first perform bitwise XOR between the two words, the output of which is sent through a NOT gate. The output of the NOT operations is then pseudo added with a fixed word, where a pseudo add operation consists of ripple carry propagation from left to right instead of right to left, which is done in standard ripple carry adders. Then the output of the pseudo add is then bitwise ANDed with the initial XOR output. Now the one of the indices of the bitwise AND output would store the bit 1. That particular index is then read out and of any of the words to determine if the word is a maximum or a minimum. Now, all these operations are performed within 2 cycles, where the first 4 operations can be performed in 1 cycle using the modified and enhanced peripheral unit of the proposed SIM fabric. Now, using the SIM architecture, we look at transient computing workloads for IPS. The first workload is cyclic redundancy check, which is commonly used to ensure correctness of data during storage and transmission. Now, the key operators in the CRC algorithm is XOR, left and right shift, and lookup tables. Now, we first perform a SIM XOR, which is immediate addressing based SIM XOR, of the first byte of the message with an initial CRC value, the output of which goes to the lookup table, and the output of the lookup table is then again XORed with the initial CRC value, which is left shifted by 8. And the new CRC value is then partially written back in every iteration for every byte of the message as shown here. The final CRC value is then XORed with the initial CRC value, which leads to the computing and checking of CRC in transient computing workloads. Now, another transient computing workload which we target is edge sensing in wireless sensory networks. The recent data-intensive workloads has led to rapid depletion of network energy and lifetime due to huge amount of processing and data aggregation required for these networks. Therefore, to conserve energy and bandwidth, it is essential to filter out and condition some of these sensor data inside the network itself. Now, the common data aggregation functions are average, minimum, maximum, sum, and variance. And in this work, we propose to perform the required data aggregation statistical functions within the memory of the sensory nodes to enable efficiency and longer lifetimes in energy-constrained WSNs. Now, first, the global sum operations are performed using in-memory addition operations, an example of which is shown here. We perform iterative reduction operations to achieve a global sum between multiple words stored in the memory array. To perform average, we use in-memory truncation by right shifting the global sum by log n to the base 2 bits to obtain the average. Number of iterations required for performing global sum of n words is log n to the base 2. A similar approach is used for performing global comparison operations to find global maximum or global minimum, where we do iterative operations to achieve and reduction operations to achieve the global sum of the sample space. Now, for various computation, we combine in-memory subtraction with in-processor operations for wireless sensory networks. Now, we design an in-house TI-MSP430 based simulation framework for the IPS SIM, where we have a custom assembler which generates instructions for in the MSP430 assembly language, and we use a parser to extract the instruction trace based on the required standard memory reads or SIM operations for a particular application. And this, in conjunction with the circuit and array level microarchitectural results, we come up with the system level evaluation as discussed in the next slide. We compared our proposed SIM design with respect to two baselines, SRAM plus NVM and Unified NVM, both of which perform environment computing. We observe excellent improvements in energy and also achieve performance boost for the proposed SIM design. We also observe that as we decrease the supply capacitance, which delivers power to the system, the number of checkpoints increases, which directly corresponds to increase in energy efficiency. We also compare the memories with and without parallelization, and all these numbers have been plotted normalized to the SIM design and observe excellent energy and performance improvements. With that, I'll conclude my talk. We propose ferritic-based non-volatile compute-enabled memory cells to perform Boolean and arithmetic operations, especially targeted for intermittently powered systems and their workloads. We look at two specific workloads, which is cyclic redundancy check for error detection and edge sensing for wireless sensory networks. We observed excellent energy and performance benefits for the IPS SIM engine compared to conventional architectures, and therefore addressing the critical need of achieving high energy efficiency in resource constrained systems. Thank you.
Okay, do you guys have any questions? Does the audience have any questions? No? Okay, if no question, then I'll bring one. Okay. So yeah, some people just send me a message. He's just getting online. So he's waiting for the question. So the question is the proposed architecture also applicable to other emergency NVRAM technology?
Yeah. So are you able to hear me?
Yes, we can hear you.
Hi. Yeah. So so the question is proposed architectures applicable for other CAM technologies as well. So yes, we can use the compute and memory fabric for different set of applications as well. But in this work, we targeted on the intermittently powered systems, which had some unique requirements because they are extremely energy constrained. And therefore, we designed this specifically for these systems. But obviously, we can abstract some of these concepts out. For example, the in-memory comparison being proposed and can also be applied for other SIM architectures.
Okay, good. Thank you. So let's move to the last paper. Okay, let me share the screen to you. Okay, the last paper, let me start it.
What we are going to introduce about improving the efficiency of power management via dynamic interrupt management. Our study saves energy without performance degradation by using interrupt management and power management, which were previously separate research topics. At first, what is power management? Data centers uses dynamic voltage and frequency scaling to manage the trade-off between the performance and energy. As shown in the figure, on-demand governor sets the VF state based on the utilization of the CPU core for energy efficiency. If the CPU utilization changes, it will affect the governor's VF decision. Second, what is dynamic interrupt management? As the network performance of the data center has improved, the overhead for packet processing has also greatly increased. Dynamic interrupt management is used to mitigate packet processing overhead by limiting the number of interrupts based on timer method. But current interrupt management, such as Intel ICCD driver, doesn't care about the core state. Energy efficiency can be achieved by controlling CPU utilization through interrupt management. Now we introduce the effect of interrupt management. Interrupt management is being used to mitigate the interrupt processing overhead. If every packet generates an interrupt, the interrupt processing overhead will increase exponentially. This makes latency-critical applications won't get enough CPU resources. Interrupt management limits the number of interrupts to process multiple packets with one interrupt. Packet processing overhead decreases as the number of interrupts decreases. However, the longer the wait time between interrupts, the more the delay will occur. Therefore, it is important to use an appropriate interrupt rate. To find energy efficient ITR, we conducted various experiments. First, left graph shows the tail latency of each interrupt management policy according to the increasing network load. As the hardware supports ITR range of 24 to 4088, but Intel ICCD driver only uses up to 336.
At the low load, ITR24 has the shortest tail latency since there is no interrupt waiting time. At the high load, ITR4088 has the shortest tail latency since an application utilizes sufficient CPU resource. Right graph shows the CPU utilization. ITR4088 can reduce the CPU utilization by reducing interrupt handling overhead. VF state can be lowered by the amount of reduced CPU utilization. We can find the chance to reduce energy consumption by reducing CPU utilization. These graphs show that an appropriate interrupt throttling rate can reduce energy consumption. We found an opportunity to reduce energy consumption between interrupt management and TOFS. To capture energy saving opportunity, we measured per packet latency according to P state and ITR combination. When operating in P3 VF state with lowest ITR, latency is greatly increased because VF state is not sufficient. Therefore, raising VF state to P0 improves tail latency. On the other hand, if we set the energy optimal ITR, such as 336 in this case, we can see that latency became low despite the low VF state. This is because interrupt management reduces interrupt handling overhead, allowing applications to utilize sufficient CPU resources. Therefore, if energy optimal ITR is applied, there is an opportunity to save energy without performance degradation. Based on the motivation, we propose iState. iState already knows the energy optimal ITR for each VF state through offline training. Power management collects the current CPU utilization and notifies the next VF state to iState. iState finds energy optimal ITR from the mapping table. iState can save energy without compromising performance because interrupt processing overhead is mitigated. To evaluate iState, we used the Xeon servers with 10 gigabits network. We modified the Intel RGB driver and Linux kernel to implement iState. We used the MapHD as a benchmark. In the left graph, tail latency of iState was not damaged in overall range compared to the on-demand governor. Furthermore, iState improves tail latency by up to 15.9 times at high lows. In the normalized energy graph on the right, the energy was saved by up to 17.6% at the high lows. We can see that the proposed iState can save energy without performance degradation for MemCached benchmark. We propose an iState which improves the efficiency of power management via dynamic interrupt management. iState improves tail latency by 15.9 times and reduces energy consumption by 17.6% compared to the existing method. This is the end of my presentation. Thank you for listening.
Okay, thank you very much. Does the audience have any questions? No? If the audience doesn't have a question, then let me ask a question. So Kidong Kang, you are here, right? So the question is, what's the offline training process? How do you make it?
Oh, okay. Can you hear me?
A little bit louder, please.
Oh. Can you hear me?
Yes, yes.
Oh, okay. Yeah, your question is of the offline training. Okay. So the answer is our iState basically checks the VF state for decision of the interrupt rate. So at first, we need to check the VF state supporting the processor. And then we set the appropriate interrupt rate by sum of VF state. So the result is the combination of the VF state to interrupt rate. And lastly, we use a simple regression model to connect the combination. And for detail of these procedures, please check our paper. Yeah.
Okay, so thank you very much. So our session actually sharply finished on time. So thank you guys for your attention. And I think there's 10 minutes break. Then you can go to the session 5B. Welcome back. So thank you guys. Bye-bye.
Thank you, Doctor.
Thank you.